This one is C9H8O3 and it would have 6 double bond equivalents. We have a 5H over here in the aromatic region, that'll be C6H5, and we have a CH3 group over here. What's left? We've got 2 C's, 3 O's, 2 double bond equivalents. That would indicate a C double bond O, or 2 C double bond O's, and an O, and everything's counted down to 0, so we probably have the right pieces. Alright, now we can put it together, and we need to figure out where the CH3 is going to go in relation to these other groupings. Now, one thing I can tell you is that the CH3 is not going to be directly connected to the oxygen. According to the correlation chart, CH's connected to O usually appear at around 4 ppm. So the CH3 group is not going to be directly connected to this O. That tells me it's going to be connected to one of the C double bond O's. I'm going to connect it over here because I know it's going to be on the end. So then all that's required is to figure out the order of the C double bond O and the O. So I'll just drag these over. So we've got to figure out, is it this way or is it this way? And initially you might think it could go either way, but we actually can get a clue from the splitting of the aromatic region. So here's what we know about ring splitting in the aromatic region, and what's going to happen is if you've got a C double bond O directly connected to an aromatic ring, it's usually going to split into 2 sets of peaks, and those will be centered at somewhere around 7.5 ppm. When there's an O directly connected to the aromatic ring, it's usually 2 peaks, and they're centered at around 7.0 ppm. Looking at our example, we can see we've got 2 sets of peaks, and they're centered closer to 7.5 ppm, which would indicate that we have a C double bond O connected to the aromatic ring rather than an O, which is why I would choose this structure as my answer.